The next channel I want to talk to you about is going to be another gated channel, but this one is going to be gated by something different. This is going to be called our voltage gated ion channels. So let's make some room for some voltage gated ion channels. There are two voltage gated ion channels in particular that I'm going to talk to you about right now, but I'm going to specify that there's more than two, and we will encounter some other voltage gated channels a little later on. Now the first voltage gated channel that I'm going to do, and we'll pick this red, is going to be a sodium specific channel. It selects for sodium. Sodium is allowed to come into the cell through this voltage gated channel. Now the channel itself is actually going to have two gates. All right, and this is an important fact that you need to remember, that there are two gates. If you've ever been to a dog park, I know a lot of you in class have dogs. If you've ever been to a dog park, most dog parks, the entrance to the dog park is a double gate system. And that way you can walk through the gate, close the gate behind you, and then unleash your dog and open the other gate. And so it keeps your dog from running away and being able to get into the dog park. So the voltage gated sodium channel has these two gates, and the first gate that I want to talk about, and every textbook draws it different, every video draws it different. I'm going to draw it my way, and the first gate we're going to talk about is a gate that's going to be found, I'll just put it right here, okay, and that particular gate is what we're going to be called, let me go ahead and number it, we're going to say, well actually maybe number's not the right way to do this, let me label it though. This very first gate here is what we call my voltage sensitive my voltage sensitive gate. The other gate, and again each textbook draws this a little different, each person's going to draw this a little different. I kind of like doing this whole ball and chain type thing going on here. And so this is going to be my other gate. Okay. And this particular gate, we're going to call this one, is going to be my, I like to call it my time sensitive. Or we can just call it my inactivation gate. And so more on this later. We're going to look and see how this works with the action potential in a little bit. Now, the voltage part, voltage refers to, let's define voltage. In our situation, in our case, voltage is potential energy. Specifically, membrane potential energy. And we measure, so we actually use volts all the time. If you look at batteries, for example, your 9-volt battery that is in common usage for various items, your fire alarm that you put these 9-volt batteries in. And what that 9-volt battery, what 9 volts is really telling you is that it has potential energy equal to this unit, and voltage is a unit, volts are a unit. And so it's essentially just saying this is how much energy is contained in this battery before you plug it in. Now as soon as you plug it in, that voltage is going to change as the potential energy within that battery is converted into kinetic energy to do work. We're going to have a similar situation here with these voltage gated channels. It's the potential energy that is contained within the membrane that causes them to open. Now, at rest, when the cell is resting, during resting membrane potential, the gate for the voltage gated sodium channel is closed. Okay, and we're going to talk about how to open that. Let's look at the other voltage gated channel that we have, and that's going to be my potassium. voltage gated potassium channel. So let's put that voltage gated potassium channel here. Now, voltage gated again, so this one is going to be opened based using the potential energy that is contained within the membrane. Okay. And it is selective for potassium. Now this one only has one gate. Okay. Only has the one gate. And so I'm just going to draw that there. So we've got a voltage gated sodium channel in red and a voltage gated potassium channel in that greenish color. And at rest, when the cell is resting, both of those channels are closed. Now here's the thing though. You guys remember these leak channels? I'm sorry, not the leak channels, the ligand gated channels. Let me go back to this ligand gated channel, and I'm going to simplify this for right now, and we will actually revisit this when talking about the action potential. But let's say our neurotransmitter comes along, binds my ligand gated channel. And what does that do? Well, you already know that what that's going to do is open the gate. And once that's open, my sodium ion is going to begin to flow into my cell. Now, take a look at that sodium ion. It carries with it a positive charge. And that positive charge, any time that you move, you cause charged molecules, whether it's electrons, which are negatively charged, or positively charged ions, or what have you, those are going to come into the cell and they provide this electrical current. And it's that electrical current, that electrical stimulation, that triggers the opening of these voltage sensitive gates. Okay? And so in response to a change in the membrane potential, these gates are going to open up, and now my voltage gated sodium channel is going to let more sodium into my cell. Okay? And that's going to further change the membrane potential of the cell. Potassium channels will also be opened based on a change in membrane potential, and those will let potassium out of my cell. And that's the very beginnings, the introductory material that you need to understand in order to understand the rest of what I'm going to teach you here. Now, before I go on to the next segment, I want to explain a little bit about location. Location is very, very important when it comes to membrane proteins, or for that matter, any of the proteins within the cell. You'll recall that in the mitochondria, we have the necessary enzymes for cellular respiration, and those are localized to that, either to the matrix of the mitochondria for the Krebs cycle, or if they're electron transport chains, they're stuffed into the inner membrane. And so we've got these localized proteins trapped together because they work together. Ion channels in neurons are no different. Your ligand-gated ion channels, and to some extent, your leak channels, although honestly leak channels are virtually everywhere, but the ligand-gated ion channels especially are highly concentrated in the dendrites. And to some extent they are also in the cell membrane of the soma. Okay. But you don't see a lot of them in the axon. On the other hand, these voltage-gated sensitive gates, or voltage-gated gates, these guys are found starting off in that trigger zone, highly concentrated in the trigger zone, and the axon hillock. And then depending on whether or not you're dealing with a myelinated or unmyelinated neuron, and myelinated neurons, they're highly concentrated in the nodes of Ranvier. Okay, highly concentrated in those nodes. If it's an unmyelinated neuron, it's all throughout the membrane of the axon. And we'll talk a little bit more about how I'm going to put everything together in a big picture so you can see this all together and you can see how the neuron works. We're going to go through that step by step. But that's the introduction to the ion channels. I think we should be good to go to dive into resting membrane potential, graded potential, and action potential.